So we've seen how the quantum model of supply and demand can be used to model transactions, and here we're going to look at how we can use it to simulate the stock market. So with the quantum model of supply and demand, we have propensity functions for the buyer and the seller, and the joint propensity function given by the solid line there is equal to the product of those, and a market maker would maximize profit if the spread between the buyer and the seller price, that distance between the two peaks, is equal to the standard deviation of the joint propensity. And this system is described by a linear entropic force, but it does not behave like a classical oscillator because we know that price is indeterminate, and of course prices don't actually oscillate. So we go to the quantum harmonic oscillator, which is the quantum version of a spring system. The ground state is a normal distribution where the mass scales with the inverse variance. And we're going to define the frequency. So for stock market transactions as in terms of turnover. So basically, if the turnover is once per year, then that will be the frequency. And this is a quantum harmonic oscillator, sort of a plot tracing its motion, where we have three energy levels. Most of the energy is in the ground state, but then we've got the next two energy levels. So that's one way that you can use the quantum harmonic oscillator to simulate the sort of statistics of stock markets, is to look at higher energy levels. We're going to look at a slightly simpler version here. But first of all, just kind of compare with the actual sort of data that you get from a stock market. So this is an order book for Apple over a single hour. And so we've got the buyers putting up orders at lower prices and the sellers at higher prices. And these are not the same as propensity functions, because these are sort of stated things which don't reveal all the preferences. And of course, orders in the middle here are going to clear and they're going to disappear. So these aren't the same as propensity functions, but they kind of give an idea of these propensity functions, which are kind of shown here, lurking in the background. So in finance, there's this square root law for price impact, which states that so let's say that someone comes and makes a very large order, and you want to know how much the price is going to change and respond to that. It's going to go up, but by how much? And so the square root law says that the price change is given by the square root of the size of the trade divided by the daily traded volume, multiplied by the daily volatility, and then multiplied by this number y, which is a numerical constant of order unity. In the oscillator models, this makes sense because the restoring force is linear, so the energy required to perturb the system is going to vary with the square of the displacement, or equivalently, the displacement varies with the square root of the energy. And of course, the energy in a harmonic oscillator, quantum harmonic oscillator, is just a multiple of the frequency. So when you have a large purchase, that's like boosting the frequency over that time period, which boosts the energy. And comparing these two formulas show that they're in agreement if we have y sort of being of the order of the square root of 2. And that sounds about right, because in the oscillator model, we're assuming that sort of all the energy goes into lifting the price. So it might actually, the actual price change might be a bit less than that. And this gives us a kind of a picture for how we could model prices in general. We can assume that we have this oscillator in its ground state, but then it's displaced by perturbations, which sort of shift it from side to side. And then when that happens, it's going to oscillate in a coherent state. And then a coherent state is like it stays in a normal distribution, but it's moving from side to side, and the probability of being in a particular energy level varies with a Poisson distribution. And so we're going to assume that the spread between between the bid and the ask price, we're going to set that equal to the standard deviation in order to, we're assuming that we're maximizing the profit here. And so that just kind of gives you a picture here. So this you have a sort of a normal distribution kind of bouncing back and forth like this between the dashed lines. And then if you trace and where it intersects, where this propensity function, which is moving from side to side, where these intersect with the bid or ask prices, are going to tell you what the bid price or the ask price is. So there's kind of the picture here is that in a way we have the buyers and the sellers giving you the joint propensity function, but then there's another participant in the market, which is the market maker, who only transacts at these particular set prices. And then if you follow, so it kind of makes sense that we got this oscillation going on. And so if you look at the propensity for the ask price being obtained, it follows a sinusoidal sort of plot like this. So the dashed line is the actual result. The gray line in the background is a sinusoidal plot of the sort that you would obtain with a simple two-state quantum system, for example. Similarly, the propensity function for the bid would just be the opposite of that, sort of going like this. So the propensities add to 1. And notice that the variation, so for this particular setting, we've got a variation going from 0.25 to 0.75, so that's plus or minus 25%, which is consistent with the kind of shift that you might expect from the quarter law from quantum decision theory. And then, so we have this model, and we can use this to simulate stock prices. So here the squares are the ask price, the circles are the bid price, and now I'm assuming that we got this random perturbation. So in the previous plot, that's what happens when you have kind of a smooth, regular oscillation. But here, I'm assuming that the oscillations are sort of not allowed to continue. We're getting like kind of random jitter, random noise being applied, and we're also going to have some noise added to the spread term, the difference between the bid and the offer. And and that actually the noise and the spread turns out to be important. It's a main contributor to these kind of fat tails, which you see when you look at the overall probability density for a long simulation. So you've got kind of sharp peaked and fat tails, which compares with the dashed line, which is the statistics for the Dow Jones Industrial Average. Okay, so to summarize, in neoclassical theory, it seems that supply and demand cancel out in equilibrium, so there's no concept of dynamics, force, mass, energy, and so on. The quantum model, in contrast, is obtained by quantizing a linear entropic force, and this linear restoring force is what explains the empirically derived square root law of price impact. And the oscillator model can be used to simulate the dynamics of stock markets, such as price change distributions.